is called Manage Your Environment with LiDAR, or mapping your environment with LiDAR. And Adam and Bruce are our presenters today. And maybe some of you remember Bruce. He retired from, or left, I don't know if he's retired, from Manitowoc County a few years ago. I don't want to make him older than he is. But some of us do that. We retire and then we come back and you find us at different places. So we're glad to have both of them joining us today. We're going to be taking questions through the chat. So send those in anytime. And Tony Rally from Calumet County is going to be monitoring them. And then at the end of the session, he'll read those to Adam and Bruce, and then they will answer them. Then we're recording this session and the CEU should be in at the end. So you'll get CEU credits for this session as well. And again, just send in your questions through the chat and watch your chat for some important links. I think we're ready to get started.
That sounds good. Thank you very much, Penny. Well, thank you everybody for joining us here this afternoon. I wish we could be in person like everybody else says. We're looking forward to seeing everybody. But today what we want to do is talk a little bit about LiDAR data. Obviously we're with Ayers, Bruce previously Manitowoc County. Ayers is a AEC firm, so a lot of architectural and engineering. But really what we're going to be focusing on today is our specialties in environmental engineering as well as our geospatial work. And Bruce and I both work in our geospatial division. Ayers is an employee-owned company. A lot of you probably know us from working on dams or water resources. But what I want to do today is educate you about your LiDAR data and how you can think about using it in your day-to-day work. So my name is Adam Derringer. I'm a senior project manager at Ayers. I came over to Ayers 9 years ago in about 7 days. I think I'll hit 9 years. Previous to that, I was a GIS manager for 12 years. I really love data analytics and trying to utilize data that exists to solve problems. And that's really been my specialty here at Ayers. And then presenting with me today is Bruce. Bruce, feel free to.
Yeah, hi, I'm Bruce Riesterer. I worked with Manitowoc County for 33 years, and I did retire, and then I started working here at Ayers. And so I've been here 2 years. It's been really exciting. I also run a small farm, so I have some experience with implementing conservation practices firsthand. And I really appreciate all the important work you do for Land and Water Resources, and it's really an honor to be here today.
Thanks, Bruce. So today we're going to talk a little bit about LiDAR. I don't expect everybody knows what it is, but it's been around quite a while. So I'm figuring I'm not going to have to educate you too much on that, but I can answer any questions you have on it. I want to talk a little bit about how you can go about viewing LiDAR data, where LiDAR data is, what things people are creating with their LiDAR data sets that exist. But then we're going to dive in a little deeper on a couple of specific topics. So that's going to be looking at county or municipal soil erosion, mapping potential inundation sites. We're going to look at how you can use it to find your closed depressions across your region. We want to talk about modeling flow accumulation, not just like on a 40, but we're talking about countywide or even regional flow accumulation models. And then utilizing that LiDAR data and analyzing it against FEMA's floodplain data. So with that, what is LiDAR? I mean, LiDAR stands for light detection and ranging. It essentially works like sonar, except it is using a laser. In this case, we're talking about utilizing a laser from an airplane. A LiDAR system can fire millions of points a minute down to the ground. And that laser pulse goes down to the ground, and like any form of light, it reflects back. And since we understand the speed of light, we can figure out a measurement for everything that laser pulse hits and returns back to the aircraft. When you get millions, billions, trillions of those points, we can start to create really, really rich, high density surfaces. So what most people originally started using LiDAR with was going to be what you're familiar with the FEMA data. You're creating new floodplain and hazard mapping. As data got higher resolution to it, you started to be able to do more detailed drainage studies. As sensors started to be able to collect more information and the software could extract it, you could do things like map your trees and map your buildings. You could analyze your terrain and your slope. You could look at things like vegetation encroachment to utilities or change detections of your forests. And then for certain projects, even in site development, you're looking at engineering, planning, and design. If that's for a dam or a building site, a utility, if it's planning and zoning. So a lot of different uses coming from that LiDAR data as people get more comfortable with it and the data gets better and better. So as I said, LiDAR data has been around quite a while. Wisconsin is a very early adopter of LiDAR, and I'll cover that a little more in a bit. But those first projects were in 2002 using these first generation LiDAR sensors. They're very, very expensive equipment. You're looking at, a $2 million sensor that you attach to a Cessna on a plane. So really high investment. But what I've found in working with people utilizing their LiDAR data is everybody thinks it only does what it did in 2002. That's not the case. You can do more with it these days. The technology and these laser sensors and the software to process it has gotten better and better over time. For example, the sensors that we've collected most of the LiDAR here in the state of Wisconsin with now fire at about 800 kilohertz or more a second. So millions of points are being collected per second. The LiDAR sensors also have the ability to fire forward and aft, so that if you've got a billboard or a series of trees or a building in the past, you couldn't get measurements on the other side of a building. You got occluded. That laser hit that hard surface, reflected back, and couldn't get anything through it. Now you've got an aft camera that can hit that spot that you missed as a plane passes over that piece. And another important part of it, especially in the environmental and built world mapping, is the sensors can actually collect more than 1 point per pulse. Think about it like a flashlight. If you've got a flashlight and I'm shining it into the woods and it sees a tree, I see a leaf, but the beam of light it hits that leaf. I see the leaf, but I also see other leaves behind it, and I see sticks behind it, and eventually I can see through the tree. The same idea happens with the new laser sensors from the planes. You can hit the top of the tree, it hits a leaf, and then it hits a branch in the tree, and then it hits another leaf, another branch, maybe part of a picnic table beneath the tree, and eventually it gets to the ground. And we can get a reading for each one of those on each individual pulse. And that makes a massive difference in the capabilities of the LiDAR data sets of today. So a little history here of LiDAR in the state of Wisconsin. Like I said, our first LiDAR, countywide LiDAR project in Wisconsin was back in 2002. And we slowly were getting LiDAR data sets brought in. These were very, very expensive data sets in the early 2000s. So we've got a couple of products that were available in 2005 and 1 and 2 in 2007. In that time, there was no standard for the data. You just had a plane and a sensor and you took what you got. Ayers worked with the DNR and the floodplain mapping group in order to try to come up with a standardized set of data accuracy as well as deliverables that could be expected. So if somebody wanted to do a LiDAR project, they had a target, like what is the minimum qualifications we need for this? So we started to standardize that information across the state. We got a big boost of LiDAR coming into the state of Wisconsin in 2010, and that really came from the floods in 2009 in southern Wisconsin. Ayers worked with a lot of the counties to apply for CDBG grants for mitigation studies. So we had several counties, about 18, just collect LiDAR data in one big boost. One of the other things I do for the state is I help run the imagery program. And in 2015, we added LiDAR to the state's imagery program. And that started adding more and more LiDAR data sets where counties were paying for their own projects. They started to realize the value of this high resolution topographic elevation data. And then shortly after that, a federal program run by USGS called 3DEP started to finally get funded. It had been around for several years, and myself and a woman named Anna out of Coastal Management decided, what the heck, we're going to write a grant for this. It was a competitive grant. We thought all the money was going to go to California and New York along the major coastlines with really expensive mansions falling into the sea, you know, along a cliffside. But we won that grant, and we've written that grant again and again and again every year, in fact, since 2015, and we've won it every year. And what that has turned into is $5.5 million in federal funding coming to counties in the state of Wisconsin. So here in 2022, we just got our LiDAR grant approved for the 2022 flights. And what that means, all the counties you see in blue on your screen right here have what we call a quality level 2. So there's this minimum base specification for LiDAR data. This is a higher standard than what existed in Wisconsin in the past. But it meets FEMA standards, meets USGS standards, meets Army Corps standards. So it's utilized by everybody in the federal as well as the state. Everybody will utilize this data for their programs. The counties you see in purple, those are being processed right now. The pink counties and the brown counties are going to be flowing likely here this spring. So as we chase that snowpack, we're going to be flying these counties. And every single county after this 2022 cycle will have LiDAR data that meets all federal specifications for floodplain mapping and a lot of other purposes. So the minimum standard for these are going to be LiDAR data that has 2 points on the ground per square meter. So if you look around your chair, you'd have about 2 points on the ground everywhere at minimum in the state of Wisconsin. Every one of those points on a hard surface has to be at least 0.3 feet vertical accuracy spec. So that's the standards that we need to meet for every one of these projects. And what you're starting to find more and more is some of these counties are choosing to collect 8 point per meter or even 30 points per square meter just to try to pull more granular data out of their program. So that leads to 1 foot contours and all sorts of other products we're going to talk about here more today. So just a quick comparison for those of you that try to use data, say back in 2005, 2010, 2013, that 1 point per meter that we used to collect at 0.6 feet vertical accuracy, this is about 1 square mile of data that you see on the ground right here. That accounts for approximately what you see in the little red box is 710,000 points on the ground. So those are surveyed points with an X, Y, and a Z. Every one of those is within about half a foot vertical accuracy. That's pretty incredible. Now, if we fast forward to 2017, so right in the middle of our 3DEP program, this is a quality level 2 standard with our brand new sensors and all of our new specs. That same tile, that same square mile, we're extracting a lot more information, but just on the ground, we went from 710,000 points to 4.5 million points on the ground. So when I say it's a denser data set and you can start to do better drainage study, that's one of the big reasons why. We're penetrating trees, we're getting around buildings and other occluded areas. So what are a lot of counties and municipalities doing with that data? Well, it really started with mapping their hydro data sets. So with that LiDAR data, we're mapping flowing streams with a Z value to them down to about 8 feet per square meter. You can map, you know, acre ponds, quarter acre ponds, whatever you want to do, just mapping really high grade hydro with it. We've been classifying that data so that we can see, okay, what are trees, what are buildings, what's ground, what else can we pull out of that data? Once you've classified that data, people are mapping 2D buildings. For counties doing 8 points per meter, 30 points per meter, they're doing 3D buildings across an entire county. We're mapping tree canopies. And sometimes that's for urban use and trying to see what's our footprint, or do we have enough shade for a walking area downtown, or are we trying to map our forestry like Marathon County or Bayfield or Ashland counties would have a lot of forestry going on. They're very interested in what does that change over time. We're doing 1 foot contours. Lately, we have done a lot of culvert mapping. We've gotten really, really good at trying to map culverts across entire counties. And I'll give you an example of that here shortly. Once you've got those culverts, we're creating our hydro enforced DEMs. You can't use your standard DEMs because it's just it creates digital dams. So you can't create your water models with it. We're doing slopes with it. We're mapping our soil erosion with it. We're mapping closed depressions with it. and accumulated flow models. And I'm going to rush past all those because I want Bruce to have time to kind of really show you what that means and how it's done. To give you an idea of just the resolution of data, we're zoomed out here pretty far. We're just outside of Hayward, Wisconsin. You can see a couple of roads pretty clearly. So you can see we're zoomed out pretty far here. But kind of in the middle of the screen, just to the left, you can see a four-wheel drive track. Now, this is Sawyer County, so this is an entirely forested area. I can see the left and right, tire track. I can see the ruts underneath the forest through that canopy. You see that little line over to the left-hand side of that peninsula right there. That's just a cross-country ski trail. Again, through the vegetation. So really, really detailed information that you can pull out of this where people are mapping their trails. Another example I like to show is, this is Calumet County. Calumet County has a lot of drumlins in it. It's pretty cool. I've got a geology background, so I really like this slide. You can see, obviously, the drumlin very clearly here, but we've stripped off all the vegetation again. So we're just looking at the ground point. So we're penetrating through the vegetation on the drumlin, and you can see right across the top of that drumlin where the glacier must have pushed a second time. You see the glacial striations running clearly north to south across this drumlin, and you can see the moraine just on the south side of that drumlin where that glacier stopped pushing again. It's fascinating to me to be able to see the geology structure across Wisconsin from this data. And again, we're just looking at 2 point per meter LiDAR here. So a lot of extra capabilities you wouldn't have had before. I had mentioned that we do culvert inventories, just jumping around the state for various projects, how people are using their data. In Fond du Lac County, they were one of the early ones that asked us to look at creating a culvert inventory for them. We did that. We mapped 33,000 plus culverts in just Fond du Lac County. We're using a laser to find these things. So I can't tell you if it's a concrete culvert or a box culvert, or if it's a metal culvert, or if it's crushed or plugged. But what I can tell you is there's a culvert. We can see the inlet and the outlet. We can figure out what the elevation of that culvert is, and then we can utilize that in order to create or enforce DEMs for hydromodeling. And this gives you an example of that. We just drop our culverts in. So that's a little purple line that you see here. If you don't have your culverts and you try to run a hydro model, the people watching this session today probably understand the frustration that is, that iterative process that you'd have to go through when you're trying to model your water as it flows across the landscape, and said, I know that the water's not flowing over the road or going into the person's yard here over in the south on the left image. There's a culvert there. So then you have to go in, burn it in, and run your model again. If you have all your culverts, you come out of the gates ready to go. So I believe with that, Bruce is going to show you a tool that we built. I really like this tool. It's called ArcGIS Online. We created a LiDAR online viewing app, and this is going to help people understand LiDAR data. It is a 3D data set, but we're all used to looking at maps in 2D. This is one of the first projects that Bruce and I had the opportunity to work on when he retired to Ayers.
Thanks, Adam. You probably noticed we're running this through a story map here today. And so we were able to embed some 3D web apps. And this first one is the Ayers LiDAR Online project that we've worked on. And pull up some, well, first of all, I'm going to see if we can go to full screen here, and then pull up a bookmark, the farm here. So one of the things that happened in Manitowoc County, and I know it happened around the state, is that we had LiDAR data, and there was only one person in the county using it because it was so hard to access it and work with it with the regular software. And so one of the things we looked at doing was getting that data so it was more available to other people on the staff around in different departments in the county. And then And then eventually we were able to start sharing things out to the public. And that's what we're working on here at Ayers now with this Ayers LiDAR Online. That same idea, getting, in this case, we're utilizing Calumet County here for this demonstration. Thanks to Calumet County, we're testing a lot of our new products in Calumet County that you'll see today here. But you can see we have the entire point cloud for the county, and we can go in here. So it's billions of points across the county, and we can go in here and toggle on and off the high vegetation, the building point cloud. We have a colorized building point layer in here. So we took the color from the aerial imagery and transferred that over to the point cloud. And so we did that for the buildings here, as well as the trees. The trees also have the color of the imagery, so that we transferred that color to the point cloud from the imagery. There's some other layers in here. The 1 foot contours, we're able to drape those over the surfaces. And it's kind of a handy measuring tool in here. We can go in and do some relative measurements. Here we're grabbing the top of that roof and then measuring down to the ground to get the height of that building. You can also just measure on the ground. So we have it's a LiDAR elevation surface that was built from the LiDAR data. If we turn on the ground point cloud, you can see the density of the data on the ground. So that's what that LiDAR elevation surface was built on, is that ground data, that ground point cloud. So there's a lot of versatility. You can go anywhere in the county and work with the LiDAR data, at least display it and then do some of this measuring. So one of the other things that we've worked on quite a bit here is getting different terrains. So here we have this slope, and I'll turn the contours off for this. And you can see here it's just a slope. We call it the slope shade layer. And the darker the color, the steeper the ground, and the lighter color is the flatter surfaces. And we have another option here of just the regular hill shade. So we have a couple of options for terrain. We put some other layers in here too. We have road center lines on the standard Ayers LiDAR Online, and then parcel overlay. So we'll take a look at a couple other spots here. This is a location where you can really see the stream meanders. And again, that slope shade really showing those, the different slopes, and it really does a nice job of outlining the bank of the channel here, so that stream is really very visible. And again, we can put the point cloud on top of that, turn that on and off. Just a quick look at a road cut here. So you can see how quickly we can move around the county and how quickly the data draws. So that's just our standard Ayers LiDAR Online project, and we have quite a number of counties that have done this. We've got some more coming online this year. So I'm going to move on to erosion vulnerability, the eval web app. And of course, this is a process that was developed by the Wisconsin DNR, and I know a lot of you have done this process. So Ayers is now also processing this data for counties, if you're interested in that. But one of the things we're looking at here is, can we put it on top of, and again, I'm using a 3D web app to show that data. Yeah, we'll just take a look here. This is their pipe. I think it's the Pipe Creek Huck 12. And this is the stream power index, on that 3D surface, that LiDAR surface. And again, as Adam mentioned, we're using that culvert inventory is critical to make this work for eval and some of the other things we're going to look at today. If I go back to that site now, if we added some of our other layers from Ayers LiDAR Online, it makes a more informational map, having the point cloud in there and the contours and that slope shade along with the eval output. And another look here at the soil loss output from eval and how that fits in with the landscape. And then finally the erosion vulnerability layer at a different site here. So this could come in handy. So it'd be, we do the eval work in order to get our 9 key element plans done, and and certainly they're used for watershed projects, but this would make the data a little more usable in a web app like this that could be used by staff and taken out in the field and working with the farmers. Okay, we're going to move on to a different project here, flood inundation. This is a project that we worked on here with our medicinal engineering group here in Green Bay. It is a flood mitigation study for the village of Swamico. And again, I'm going to pop out here to the full screen. And you can see where we are here in the Bay of Green Bay. They were really looking at some of the road sites along the bay here and looking at different flood levels. So, we did static maps, but then we also did this 3D application to help show those flood levels. And here you can see we have these different elevations. So we have 1/2 foot increments that we set this up on. So we can click, and as you see that the different inundation levels at this roads or at this site and what that looks like. So this was really helpful to go along with the study. And here you can actually see that when this photo was taken, how the road was wet here, recently been wet. So you can see how that fits with those flood levels that we established using the LiDAR data. And initially we were looking at just doing I think there were 6 sites that were contracted for, but then we ended up just doing the entire village here of Swamico for this project.
The goal really there was to use even as a public interface is talking about raising that road up. How far would we need to raise the road to protect those homestead sites and protect the road so people could come and go? Obviously it was Lake Michigan's not rising as much as it was, but when we first took this on, it was a real concern.
Okay, then moving on to closed depressions. So again, Calumet County, using it as the demo here, we're able to do closed depressions countywide, and there's over 10,000 depressions mapped here. Let's take a little closer look. So what we've done here is, again, using those culverts. It's important that we've got those all accounted for. So we're trying to remove all those artificial or digital dams in the data, so that we're really looking at, these are true depressions, whether they be natural depressions or a created depression in the landscape, or a man-made depression. So we've got these. So the darker the color, the deeper the depression, and then we've also incorporated this slope shade in, so you can see some of the landscape with that shading that we're using for the depressions here. And in addition to mapping, we have the perimeter here mapped of each depression and the size. So this one's 3.2 acres, and then we have the low point of each depression. And here we're using this graduated symbol to show the depth. And again, we can go in there and measure. If we could grab the bottom of that low point there of the depression and then go out, to the edge. So this would be the high point where that depression is full. And So it shows you that the depth and the low point of each one of those locations. So this one, this is an area where there's pretty shallow to bedrock, and you can see when we turn here the photo on, you can actually see some rock at that spot there. And I'm just going to jump over to a woodlot location here. So this, this one is probably not so obvious being in the woodlot, but we've got really great data even in these woodlots with the LiDAR. We can turn the trees off here and see where the detail of that depression, and it looks like maybe there might be a potential sinkhole there. So I think, I know your last session was all about groundwater, and closed depressions are important for in our 151 administration. And, there's some other things, like for land development and just the flooding potential of land that they would be important to know, but certainly something that's being paid closer attention to these days are these closed depression. And let's see, so we're going to take one last look here, and then, yeah, some contours on here. Okay, so let's move on to flow accumulation. So flow accumulation, something that I know some of you have worked with in the past with some of your modeling for runoff and designing practices. So the flow accumulation process, we're trying to run this now for the entire county. And here, in this case, we did Calumet County. So each one of these squares would be about 4 square feet for the digital elevation model in Calumet County. So there's over 2 billion of these cells that needed to be processed to do a countywide project of flow accumulation. So first there's this flow direction process, and then a flow accumulation along with some others. But it's quite a processing challenge. But we were able to run the entire county and come up with a flow accumulation model. And I'm going to pop out again to the full screen here. So we can take a look at, these are the lines at a 20-acre accumulation. We'll zoom into a site here. So one of the things that we wanted to do was take that from a raster product to a polyline. So we were able to take those rasters and turn them into polylines, and then put an acreage accumulation number on the line. So this is the accumulation of acres at different points along the way here. And we've got an arrow showing the direction of flow for each one of those spots. And as you'll see here now, we're sorting this down to 5 acres. So now these lines are starting at 5 acres of accumulation. And we ran it all the way down to 1/10 of an acre countywide. And so it turned out for Calumet County, there's about 22,000 miles of these lines that were produced for the flow accumulation. And then once we had the flow accumulation, we did create some catchments. So these are your watershed breaks. And we have 3 different levels of catchments. Watershed breaks or drainage divides. And so we did this large, medium, and small. So at the county level, zoom out here to the countywide catchment. We ended up with 43,000 catchments countywide in Calumet County. Taking another look at these flow accumulations, we needed the culverts to make this happen, that LiDAR surface. the depressions needed to be in place, and then we could finally do the flow accumulation. So we were able to get flow accumulation running into these depressions and then some flow within a depression. So here you kind of see flow, we got water flowing into this depression and then into another. So we've got flow through a series of depressions. So we got the arrows are helping here to see where the flow is going in, and then here's where the flow is flowing out of that depression. And here's the flow coming out of this depression here, and then with the acreage and the direction of the flow on it. So, and I'm going to turn the catchments on here again. And you can see the catchments, the watershed divides for those depressions and the channel flowing downstream from there. So these continue on downstream until you hit a break line. We didn't try to map flow through these perennial waters, but we do have that flow going down to those break lines. And take a look at a wooded location again, to see that we really got good. We have good data even in these wood lots, and we have some nice, some really good flow accumulation lines even within the wood lot here. Then pertaining to the work that a lot of you do, this is looking at a site here in the field, just to see the fit of that flow accumulation. This field, or this photo, this image really shows the stain on the field there. It shows where the water flow is, and I can turn this on and off, and you can see how the fit of that flow accumulation is very, very accurate. And looking at farmstead runoff with these flow accumulation lines and catchments, having this data available before you would go to the farmstead would be really helpful. Here, the manure storage, that qualifies as a closed depression. And for each one of the manure storage facilities, then we've got, here's the spot where, if there was an overflow based on the LiDAR data, here's where it would be. It rounds up to an acre of flow that would come out of there. Here we can see that, that closed depression is 0.8 of an acre. And at the time of the LiDAR data was taken, there was 4.9 feet of freeboard in there. And so you can see how this is showing, the different flow paths through the farmstead. And I'm going to turn the color on here. And here, you can see that the feed storage goes off in two different directions. We've got a barnyard here. You can see where that runoff goes. Here it looks like this could be a kind of a error here, but actually when we look closer, looks like there's a culvert underneath the building here. So that flow is going underneath the building. So we can see, the flow paths and those drainage divides for the farmstead here. Just taking a look at one more site here with the flow accumulation. It's an interesting site here with a lot of channels close together. And then on this one now we added the slope ranges. This is one of the other things that we're trying to get out of the LiDAR data are these slope ranges. So here the yellow is 6 to 12%. And then the orange is 12 to 20, and then the red is greater than 20%. So for your work, your conservation work, I know those slope ranges are important. And then of course, in the zoning, they use a lot of those same ranges. So that's another data set that we've created countywide. And you can see how that fits with the flow accumulation. Again, we could turn the contours on here. And you see how that flow is running perpendicular to the contour lines. And then our last one here is the FEMA flood hazard viewer. I know there's a lot of 2D flood hazard viewers around, and we're trying to put this now into a 3D viewer. And so again, for Calumet County, we have a site here we'll zoom into. So we took that 3D LiDAR surface and the FEMA data, And now what we can do here is grab this line, this base elevation flood level 842, and use this elevation profile tool. And as I'm going along here, we can see how that flood elevation compares to the floodplain here, the elevations in the floodplain. So it gives you the shape of that floodplain, and then how it gives a way for counties to check to see how accurate these elevations are compared to the LiDAR surface. And so that works with these base flood elevations as well as the cross sections within the FEMA data. And again, we can just take a look how that looks with point cloud data added to it. Okay, I think we're getting close to our time here, but we would be glad to take any questions at this point. There's some out there. Maybe there's some in the chat.
Okay. Yep, there's a few in the chat. The first one is from Aaron O'Brien. Availability of hydro-enforced DEMs or the lack thereof is a critical barrier to the type of hydrologic assessment and restoration work that were the focus of this morning's sessions. Can you speak to the time and expense of producing that data and what types of investments or efforts would be needed to produce that data statewide?
I can take that on to some degree. We've probably got, at least for our method of culvert inventories, it's a relatively new product, and just educating people on it, making sure they understand the ROI. But we've probably done 12, 15 counties in the state of Wisconsin for these culvert inventories. Somebody else had asked the percentage that we're capturing. We say 90%, it's probably closer to 98%. We capture culverts that are even out in the woods, but there are old forestry road culverts that are completely crushed that, we can't find, and we will miss a couple. The costs can really range. It's based on the size of the project area. It's a semi-manual process, assuming you've got the LiDAR and hopefully imagery to utilize. It doesn't cost like 18 times more than LiDAR. It's just a portion of another LiDAR project. But really it comes down to, what does the landscape look like? How big is that project area? We've talked with Melanie Coles and some of the programs going on with coastal management. A lot of those points are being collected just as a point, and that can't be used for a hydro-enforced DEM. And the cost for the hydro-enforced DEM, assuming you've got a 2D line, or actually a 3D line, right? So you've got the beginning, the inlet, and the outlet, and it's running ditch to ditch to make sure your model works right. And you've got that elevation on it. The hydro-enforced DEM, that's a pretty minimal cost, a couple of grand. It's just processing the data. So pushing in a couple terabytes of data and letting it chunk over a weekend for the most part, and then doing some cleanup at the back end.
Okay, thanks, Adam. I'm going to skip down. There was a couple of questions in here that were answered in the chat, but I'm going to skip down to Paul Tollard. What rain event size was the flow accumulation run with?
Yeah, okay. It's a full flow. So there's really wasn't a rain size event. So that, you could take this data, that watershed size and your slopes and put it into a different model. And then that's when you would use that storm size. This is just full flow. All those depressions are full when that model is run. So there's really no storm size factored in there.
Time for another question.
Thanks, Bruce.
Sure. Oh, okay.
I'll just go back to a couple of the other ones. Greg Bannock had asked, is culvert inventory sensitive enough to give pipe size? And I think, Adam, you did answer that one. You could measure the channel into the culvert, but could not 100% say that it's a 36-inch culvert.
Yeah, that's right. We're using the laser and imagery. Typically, what we've done for a lot of municipalities and counties doing this is you've got 98% of your culverts there, and how so many people do their inventories is they just drive down the road. Maybe they use an intern and they're looking out the side of the road to think, hey, there might be a culvert there. They go to a GPS point. For this, you would set up a collector app. So you'd already have all your culverts inventoried, and now you go and inspect them with this app. So you'd actually have a GIS app sitting in your hand with a cell phone that tells you, where do I go? I show up there, I've got a form. I can say, all right, it's concrete, it's metal, it's crushed, it's plugged, the size, it's a fish passage, whatever it is that you're trying to do with it, you'd put that into your form. But at least now you'd go there and inspect it and you know where you're going. You're not just mapping the 3,000 culverts on your town roads or something. It's all of them. Like I said, Fond du Lac had 33,000 culverts. Calumet had 18,000 culverts that we were just looking at.
All right, thanks, Adam. Penny's put up the code on the screen here. It's 2:01, so I think we're on a 15-minute break until the next session.
Really appreciate everybody coming in and listening to us. Good luck with the rest of the conference. Really hope to see everybody in person next year. But great job, everybody. Thank you.
Thanks, everybody.
Thanks, everyone. Yes,
Thanks again,
and
guys.
we'll be back like in 15 minutes at 2:15 for Wisconsin's changing climate impacts and adaptation strategies. Okay, thanks, Adam and Bruce. That was great. Very interesting and cool stuff. Okay, take care.
Okay, you too. Yep.
Bye-bye.
Hey guys, can you hear me?
Yep.
This is Shane from Wood County.
Yes, hi Shane. Yeah.
How you doing? Hey, wondering if you'd field a question for me quick. I was kind of waiting for the chat questions to end and maybe have an opportunity to ask my question. But so we're one of the pink counties. Adam came and gave a presentation at our county. It was a wonderful presentation, similar to what you guys did today. And we are moving forward with our 2022 LiDAR flight in the county, part of the LiDAR grant that got approved. And I'm looking at the list of deliverables. We're going to look at some after the fact deliverable packages that Adam is offering. One of the things that I've struggled with, and I came from an engineering technician background before I came county con, I still got some of that engineering blood in my veins, and I still occasionally do